Hello, hello. Good? Hello and welcome everyone. I'll probably give it 30 seconds more and then we can get started. Hey, thanks, and thanks for being here in person, seeing a lot of you after a long while. Very, very excited. Life is back to normal. I've been to many KubeCons in the past, so I think after almost a 2-year gap, right? This is starting to feel things are coming back to normal, right? Bit about myself. My name is Animesh Singh. I'm the CTO for Watson AI and Machine Learning Open Technology, and today's session, we are going to talk about how to serve machine learning models at scale using KServe. And for those of you who haven't heard of KServe, I'll go into it a bit as we proceed through the talk. Right. So to begin with, one of the things which we are seeing that around 90% of the corporate AI initiatives are still struggling to move to production, right? And not only move to production, even if they are moving in production, there is a lot of skepticism around, are these models giving predictions which can be trusted? How do we measure business KPIs? But large part of the leg up is essentially, in terms of taking these experiments which are happening within, large number of enterprises, but then, deploying them in production. And I think, as we can see, right, the proliferation of models is everywhere, right? More and more we are seeing them actually, being used in, for example, when you are playing your next song on Alexa, right? You are essentially, behind the scenes there is a model which is determining, okay, what is the next song you will like, right? And then in some cases, right, even in very important situations, like when, example, you are submitting your resume, some companies have started employing, right, AI in terms of making sure that your resume is getting to the right person or not. So these models are making, and have started making and progressively will be making more and more life-changing decisions for us. But, how hard is actually to do production-grade model inference, right? What are the things which are needed, right? One thing which you definitely need to consider at the very beginning is the cost, right? Models run on expensive hardware, GPUs, TPUs, and you want to make sure, they're not over or under scaled. You want to be able to monitor their endpoints. Are they healthy? Right, you want to be able to roll out new versions of the model because machine learning is very experimental. And while rolling out, you probably want to swap and send only a percentage of the traffic. Once they are there, you want to be able to send, inference requests using HTTP, Kafka, gRPC. And then, when we look at some of the more machine learning capabilities, specific capabilities which need to be there, like how do you do batch predictions, right? How do you have a standardized data plane protocol so that if you have written clients which are talking to these models, you don't have to rewrite them when you're moving your models from Azure to SageMaker to Watson, right? So you want to have that standardization in the industry around that. And obviously, you want to be able to serve multiple kind of frameworks like TensorFlow, PyTorch, XGBoost, right? And not only that, I think, once you have deployed your models and you've figured out, that they are running in production, you want to be able to monitor them because models will have drift, right? There will be anomalies. You want to be able to make sure that the models are not giving biased predictions. You want to ensure that your models are not vulnerable to adversarial attacks. So you essentially need very, very strong, capabilities around monitoring and metrics. And last but not the least, you also want to be able to bring your own pre-processes and post-processes because most of the models typically take tensors in, give tensors out, while from an end user, you're probably taking an image, you are taking a text, you are giving back an image or a text, right? So you need to have pluggable pre-processes, post-processes. So KServe essentially is a project which handles all of these problems and more, right? It gives you solutions and answers to all of this. It's a standard model inferencing platform built on top of Kubernetes for Kubernetes, right? And standards is a keyword, right? And definitely, Kubernetes is the ecosystem on which it is being built upon. So essentially, what are the capabilities at a high level? By virtue of it being on Kubernetes, run it anywhere. You're not getting any vendor lock-in. Standardized inference protocol, that means, you can move across multiple cloud providers or even ML providers. So for example, at this point, NVIDIA's Triton server, PyTorch, TorchServe server, Seldon's ML server, all of them are actually following this protocol. Watson is implementing this KFServing v2 protocol or KServe v2 protocol. So, there is a huge emphasis on standardization and multiple of us are coming together and ensuring that is happening. It has built-in serverless capabilities. So that means, you can auto-scale and you can scale back to zero, right? And then obviously a lot of these pluggable metrics which you can bring. Metrics around bias detection, adversarial detection, explainability, drift detection, anomaly detection, and more advanced deployment so that, when you are rolling out new versions or doing canary deployments, A/B testing, pin testing, you are getting these capabilities out of the box using KServe. Now, when you look at the architecture, I think the things typically, it looks like standard Kubernetes architecture. On the right side are essentially the things to focus. Predictor, essentially by virtue of its name, is the component which takes in the inference requests and gives you the response. Transformer, as I was talking about, models rarely will take inputs in the form you want and give outputs in the form you want. They essentially, for example, will take tensors in or give tensors out, and you need to have capabilities to plug in your own pre-processor and post-processor, so transformers bring that capability. And last but not least, the major piece, which we call the explainer, which is around all the metrics and the monitoring, right? So it explains your model predictions. Not only it explains, it gives you all the advanced metrics around drift, anomaly, bias, adversarial robustness, etc. So, as I said, you probably wouldn't have heard of KServe, but, I think quite a few of you would have heard of KFServing, right? So essentially, KServe was previously known as KFServing. And if you go back a bit in the past, it was in KubeCon December 2018. Myself, my colleague Tommy Lee, we gave a talk in terms of how to serve models using Knative and serverless paradigm. At the same time, Bloomberg was also experimenting, how to actually use serverless paradigms and build a model serving platforms on Knative. And then in July of 2019, we got in Google office in Sunnyvale with Ellis and some of the folks from Google. You probably recognize David, the Bloomberg folks, the Seldon folks. We all got together and brainstormed and started creating and putting this platform together. We released it in September and November of 2019 at another KubeCon, right? We actually launched it in a big way, where there were quite a few talks, all standing only talks, very, very packed, as you can see from the picture, right? So that went out, and that's KFServing, and that's probably when the pandemic happened, right? Probably one of the big conferences after which things went into a bit of limbo. So then here we are, approximately 2 years later, and what has happened? This, right? So KFServing is now KServe, and I think our reasons, it was not just, dropping that F, but primarily what we started seeing, right, the project started growing a lot. There were a lot of capabilities which started coming in. And as part of that, right, the repository started becoming a monolith, right? And we wanted to make sure that, it can grow with the scope, because as you heard, there are a lot of capabilities to deploy your models in production. There are capabilities to monitor your models in production, the metrics, and for that, it made sense for this project to be its own independent GitHub organization. So while we were doing this, right, we ended up renaming it as well, made the name shorter and sweeter, and here it is. It's called KServe. So if we summarize, in general, the story of KServe, December 2018, when the first, set of presentations, demos, concepts started going out at KubeCon, and until now in September 2021, where, the project which incubated in the Kubeflow umbrella is now in its own independent GitHub organization, and it's being called KServe. Okay, so yes, this was not our reason, right, to rename it. Like, I got questions from quite a few folks, but definitely, it's not that, hey, all the projects with the word flow are out. But yeah, who knows, like, we'll start seeing projects more with quantum ML, quantum AI moving forward. Now, in terms of the contributors, right, a lot of the companies are contributing majorly, obviously, be it IBM, Bloomberg, NVIDIA, Selden, Erecto, Facebook. We are getting contributions from all across the community, and that's what makes it such a robust and strong project, right? It's not a single vendor-driven project. The community is coming along, either as users or as contributors, and helping shape it. Now, when I say helping shape it, that also is leading to the standardization, because, we were very clear from the beginning that we wanted to create a standards-based platform, model serving platform, right? So one of the things which we are doing around standards is essentially, what we call the KServe protocol. Currently, it's KServe v2 protocol, which essentially, a lot of these major providers in the industry are already following. For example, as I mentioned, and as you can see on the slide, NVIDIA's Triton inference server, the PyTorch from Facebook, Selden's ML server, they're all implementing the v2 protocol. We at Watson are implementing the v2 protocol, and what that gives you is that, if you're writing your clients talking to this protocol, you won't be worried when you're moving your models across platforms. Now, what does the protocol actually provide? It has a lot of, standardization and metrics and APIs around, to check the health of the model servers, to check the health of the models itself, and obviously to do prediction. And we also intend to evolve it, beyond just the prediction, right, in terms of explainability and other things. Now, talking about explainability and metrics, some of the projects, Linux Foundation AI projects in trusted AI space, like AI Explainability 360, AI Fairness, Adversarial Robustness, they have been integrated into KServe and made available. So if you want to build your AI using trusted and ethical means and capture those metrics, those capabilities are available as well. And not only that, right, you have more advanced capabilities around outlier detection, adversarial detection, concept drift, right? So there are a lot more metrics you can capture as part of this platform. Okay, so far so good, right? So the project has been there for around a year and a half. A lot of people are actually using it in production, right? In fact, running at a very, very large scale inside Bloomberg itself as well. But then, we started seeing some of the new scalability problems over the course of last year. Now, what are these, right? So typically, when you look at how the models are packaged inside KServe, there is what we call an inference service, right, which gets provisioned on a per pod basis, and that's where your model lies, right? So typically, conceptually, you can map, a model to a pod or a model to a container in that context. Now, what happens is, Kubernetes cluster as its own started imposing, quite a bit of these limitations, right? There are limitations around compute resources. There are limitations around, maximum pods, the number of IP addresses. For example, typically each inference service has a sidecar, which has a overhead of around, half a CPU or of half a gig of memory. And if you are having 10 models, you are replicating that overhead 10 times, right? So then you are looking at 5 CPUs and 5 gig of memory for 10 models in that context, versus if you pack these 10 models into one single inference service, you can reduce that overhead a lot, right? So that is one of the things, right, which actually started happening a lot, where we started running into these limitations around how much capacity we have and how much models we need to provision. The second thing is around, some of the Kubernetes best practices. Now, typically, Kubernetes recommends around 110 or 100 pods per node on an average. So for example, if you have a 50 node cluster, you are looking at around 5,000 pods. So at the most, even if you have a model per pod, at the most you can, on a 50 node cluster, you can provision around 5,000 models, which is very, very less. Now, in real world use cases, you're not even having one model per pod because a model comes with its own replica. Then there is transformer, right? We talked about the preprocessor and post-processor. Then there is the explainer, right? So each model on an average is around 4 pods, right? So you're looking at the most like 1,000 models in regular scenarios, right? So we can see that, we are hitting these limitations, and obviously, that coupled with some of these things that, each of these things, when you are going with a per pod or a per container paradigm, these IP addresses you can assign to these replicas of models, transformers, right? That's also becoming a bottleneck. So many of these scalability issues we started seeing at very, very huge numbers, and these numbers we are talking, at much larger scale. So essentially, that's where Model Mesh comes in. Right, and Model Mesh is a platform which has been running inside IBM Watson for quite a few years now, and it is actually the backbone which serves a lot of the Watson models. For example, Watson speech to text, Watson NLU, which is Watson natural language understanding, Watson discovery. So it has been in production, for quite a few years, and it's essentially the de facto model serving management layer for IBM Watson products, right? And what it actually gives is essentially a high scale, high density use case, right, for frequently changing model use cases. So if your use case is where you have hundreds and thousands of models, right, probably, small to medium sized models, and, they are being used in very random fashion, this is a perfect platform where you can actually do much more with much less, right? And it does it by doing an intelligent trade-off between, how it responds to users within, very, I would say, milliseconds response time, and then, how does it actually calculate the computational footprint. So this is the architecture for Model Mesh. Now, typically what you see here are the pods. Pods are the ones which are essentially holding your model serving runtimes, right? So for example, if it is Triton server, the pod is actually running that Triton server, or it can be running a Torch server, or it can be running the ML server for scikit-learn and XGBoost models. And then there is a sidecar called Mesh, right? And Mesh is where, the most of the intelligence is, in terms of how to do placement, how to do routing, how to create that LRU cache. So essentially what Model Mesh does is treats your whole Kubernetes cluster and the pods pre-provisioned on it as a distributed LRU cache, least recently used cache, and then uses that to actually place these models. Now one of the things which is also in this architecture, as you see, Model Mesh also brings in its own etcd, right, and it uses it to store a lot of the metadata around these models, and it is not relying on Kubernetes etcd for quite a bit of these things. So when we look at the Model Mesh GitHub repository, there is the Model Mesh serving, which is the controller, Kubernetes controller for admitting your models, reconciling them, right? So it has all the logic, the Model Mesh itself, which has all the logic and the intelligence to place and route requests to your models. And then the runtime adapters, which are essentially serving many functions. One, for example, they are the ones responsible for, pulling your models from storage and then presenting it to the runtime, right? Whether it's the Triton inference server from NVIDIA or the Torser from PyTorch, right? They actually present that in the format in which the model server expects. So currently, out of the box, these are the two model servers which are supported from Model Mesh, the NVIDIA's Triton Inference Server and Seldon's ML Server. The next which we are going to add support for is PyTorch from TorchServe. But there is a custom resource, right, which somebody can extend and add support for their own model serving server if they need to. Now, okay, so Model Mesh does all these things. How does it do it, right? So there is cache management and high availability built in, right? So for example, as I mentioned, it treats the set of pre-provisioned pods on a Kubernetes cluster as a LRU cache, right? And then, it decides when and where to load and unload these models, right? And how does it decide? It actually takes into account two factors, which is the cache, right? The cache usage as well as the request count, right? How many requests are coming versus, which are the least recently used models, right? These are the two key things which go into their decision making. And once it has, deployed your models, it also acts as a router, right, where in terms of being able to load balance the request across them. It also has intelligent placement and queuing, right? So as I was saying, the placement essentially is happening, using both the cache age as well as, the request load. Both these parameters are used. And then it has inbuilt queuing, right? So if a lot of concurrent requests are coming in at one particular time, it will actually queue your request. But it also gives you capabilities for priority queuing or, being able to jump the queue if some request is at a high priority. Now, if you're looking at a lot of these functionalities, right, there is not only, intelligent calculation in terms of the placement using the LRU cache mechanism, there is the routing and load balancing, there is queuing. You possibly, if you're building a project in Kubernetes community using these functionalities, you are looking at combining 3 or 4 different projects, right? And that's the great part here that, all these capabilities come into one single compact platform into Model Mesh, right? And there is resiliency built in as well. Now, so the first thing is, okay, you have been able to deploy these models. What about day 2, operational simplicity, right? How do you actually roll out new versions of the model? Will it allow you to roll out new versions of the models, right? So it actually supports, rolling update. Automatically, you can roll out new versions of the model. It uses this concept of, vModel endpoints, which are then shifted to your new versions of the models once they have been loaded into the cache and they're active and serving the requests. And last but not the least, the scalability, right? So Model Mesh essentially, can support hundreds and thousands of these models in a single production deployment of, for example, 8 pods. Yes, you can have just 8 pods running and be able to serve hundreds and thousands of models, right? And we have seen this in practice. In fact, we have been doing some just experimental tests outside of Watson just to see on a single node cluster, right, which is a Kubernetes slave machine, which has just a single node of 8 CPU and 64 gig of memory. We can actually deploy up to 20,000 models in a very fast manner and get, for the most part, single millisecond digit response time, right? In some cases, yes, the response time goes into double-digit milliseconds, but for the most models, this is a single node cluster we are talking about. So as part of this, what we are announcing, one of the things which we announced at KubeCon and the announcement went, just yesterday, is essentially we are contributing Model Mesh from IBM Watson to open source. And as part of that contribution, we are actually combining it with KServe project, right? So now you have a single project which will provide you interfaces and APIs and a standard way to deploy in Kubernetes for both a single model per container paradigm as well as multiple models per container paradigm, right? So depending on your use cases and needs, you can choose either. And in fact, it's already available. So we just cut the KServe 0.7 release yesterday, and Model Mesh is available as part of it. So now as part of this, you have a single inference service custom resource, which you can use to deploy models not only on the traditional KServe single model paradigm, but also, on the Model Mesh if you want to pack it with multiple models co-residing on the same container. Looking at some of the roadmap, some of the items which we are currently focusing, obviously we want to improve the storage support. We are actually working on, enabling multi-namespace support for Model Mesh. But Q1 of next year is when we want to get all the capabilities which are available for single models in KServe, and if you are using them, available with Model Mesh as well, which includes, canary rollouts, transformers, and then bring more advanced capabilities like transformers, which allows you to chain multiple models together, so that, the output of one model can be fed as an input to another model, and you can create a chain of these models together. So all these capabilities, what we are targeting for Q1 of 2022. Okay, we'll probably do quick demo of Model Mesh, and then I can take some questions. We're running good on time here, so let me see if this is. So this is essentially, as I mentioned, some of the experiments and the tests we were essentially doing on a single node cluster, right? So this is a cluster which has just 8 CPU of memory, 8 CPUs and 64 gig of memory. And that's essentially, the place where we are launching some of these models. The other thing which you see is around, for example, the number of pods we are running. So only 2 pods in this case. So these are the pods, right, which are the Triton server from NVIDIA, which we are running. So very fairly small deployment in this particular case, right? And when you look at the number of models deployed here, we have already deployed around 15,000 models currently, right? So looking at the Grafana dashboard from here, yeah, so around 15,020 models are already loaded and managed. So there is, now these numbers are same in this context, but what that typically means is, 15,000 models are registered and 15,000 models are actually available through cache. Now, if you look at the cache graph, we essentially have assigned just 2.5 gig or 2.75 gig, I think, in the context of these two model servers, right? So that's the amount of memory which is available to serve these models. And all of these models are loaded within that particular context. Now, when you look at the numbers here, like how many models are available on per Triton server instance, the math is more than 15,000, right? Because some of the models have their replicas which are deployed across both the pods. And the other thing which you see is, you don't see any activity on the serving runtime model loading rate or on the cache miss rate, right? And there is no request being sent. And the worker node CPU is, utilization is pretty small. This is the, usage of the controller where the model mesh controller is running, pretty small at this point as well. And if you see the memory usage, both the Triton servers are taking, most of the memory. So one thing which we will probably do at this point is we will launch, this is a Kubeflow pipeline, right? So if you're aware of the Kubeflow umbrella, there are different projects. Kubeflow pipeline is one, another project, and we have use a version of Kubeflow pipelines which we have written to run on top of Tecton, right? So we will use to actually deploy some additional models. So 15,000 models are already deployed, right? One of the things, other things which I wanted to highlight, right? 15,000 are deployed, out of which around 5,000 are very simple string TensorFlow models, and which you see here, simple string TensorFlow models. And then I believe there are 5,000 Onyx models. Yes, so there are MNIST Onyx models, 5,000 of them. And then there are 5,000 of PyTorch models. Yeah, so PyTorch CFAR models, right? So all these different kinds of varied models are deployed, total 15,000 on this cluster. And I'm going to deploy a few more, right? Now, typically, when I'm running these tests, I run, typically deploy 2,000, 3,000 all at once. Here, because we want to finish this in time, right, I will just push 10 more at this particular point in time. But what I will do is, send payload. After deploying those 10 more models, I will send payload to around 1,000 of the models in together, right? So 15,000 models are already deployed. I'm going to deploy 10 more and send payload requests to 1,000 more models and probably send it for, let's say, 90 seconds. Okay, so I launched this pipeline. So I think, again, if you're familiar with Kubeflow pipelines, right, this is hopefully not net new to you, right? So this is a Kubeflow pipeline which runs in components. This is the first component which is deploying. So it will start streaming the logs, it is going to deploy these models onto that cluster. Yes, and now one of the things we will see is when we go on the Grafana dashboard, right, to see, we'll start seeing, as this rolls out, right, it actually goes ahead and starts deploying these models. We'll see, some of the activity on some of these graphs tracing, right? So essentially the CPU percentage, for example, on the controller is getting increased. Now the number of loaded models, as you can see, is increasing as well, right? The managed and loaded models. And then what you see is, some activity here in terms of the loaded models, right? So it's trying to now load new models because the second, those 10 models are being deployed. The second thing which is happening is after those models are deployed, we are sending payloads, right? So I talked about we are going to send queries to around 1,000 of these models, and we'll see. So as you can see, now these graphs and dials are showing, right? So this is actually, serving at this point, if you see around 200 queries, or 200 inference requests which are coming. Now, if you see the request latency, it is all in single digits, right? This is all showing 4 milliseconds, right? So for the number of requests which we are seeing, around 1,000 concurrent requests for a couple of minutes, we are seeing a single digit millisecond digit response time. And this essentially, is essentially just showing, how much each of the Triton inference servers, how many concurrent requests they are handling at that particular point in time. Right, so hopefully this gives you some of the capabilities of model mesh. Now there are other things which, as I was describing, which I wanted to show, which are typically edge case scenarios, right? Let's see if we can replicate it. For example, one of the things which you don't see is model unloads. And the reason model unloads are not happening is because, our cache is still not full. So if you see, like, for the total cache capacity we have applied to model mesh, to the LRU cache, it's still running at this particular level, right? So hence, it doesn't need to push out some of the models. Otherwise, what will happen is, when you're pushing new models, it will start pushing out some of the least recently used models, and that's hence the name, LRU cache. The models which haven't been used of late, start pushing out, and you'll start seeing activity on this model unloading rate. The other thing which might happen is also, the cache miss rate, which is essentially if you send inference requests for models which are not available in the cache, you'll start seeing that the cache miss rate as well. So let me launch one more pipeline just to see if we can hit, any of the models which are not in the cache. This one just ran, and it completed. This pipeline got completed. So as you can see, more than 50% of the models got around 4 millisecond response time. For 95, more than 95%, right? There is 24 millisecond response time for this particular use case. So fairly good, right? For the number of models which we have in that cluster, which is now running at 15,000 plus. Okay. Here we will try and send payload to all the models, right? So I'll choose an experiment. I will run it in my payload duration in second. Let me make it 2 minutes. Payload queries per second. Let me make it 50. And we are sending, payload requests to all kinds of models, like the TensorFlow simple string model, the PyTorch CFAR model, and the ONNX MNIST model, right? And I start this particular pipeline. Again, as soon as it starts executing, you'll see, it will start pulling out some of the logs. Okay, it started creating the request. And hopefully, we'll see some of these requests spiking up. And maybe if it starts hitting some of these models which are not available in cache, we can see, some of these cache miss rates available here as well. Okay, and while this is going through, I think I can take certain questions. So if there are any questions folks have, please bring it up. Go ahead. Yeah, go ahead.
Do you want me to repeat it, or?
I think there are people watching online as well, so it will be good for their benefit, right?
Okay, sure, yeah. So my question is, somewhere you mentioned that you're running around 20,000 model on an 8 CPU machine. So I'm trying to understand the use case, because in this case you kind of running 0.0004 CPU for each model. That means most of the time models are sitting idle, right? So in what scenario you would like to have this?
You're talking about this
function? Like, why you want to load up so many models in so much less CPU or smaller footprint?
Yes. Like, so yeah, if you see, like, so how does model mesh handle and provide you so much scalability is essentially, by overcommitting the aggregate available resources, right? Now, so we have been running this in production for many years, right? And a lot of the models like Watson speech to text, NLU, etc., which are running in public cloud scale, more often than not, what you see is, when you have these hundred thousands of models, right, not everything is getting used all at once, right? You're getting, based on different scenarios, based on different use cases, based on a particular time of the year, a particular set of models are being hit heavily, a particular set of models are, not being hit heavily. So this kind of scenario works very well when you have these hundreds and thousands of models, small to medium size, right, which you need to run and deploy. And typically think of them as being registered, but they don't need to be active 100% throughout the year. right? They are getting these requests, right? So that's where it shines. Now, so how it actually does is essentially, the cache, the LRU cache is essentially, it has a list of the models which have been deployed recently and how often they are being used. The ones which are being used least recently, or the used ones, they are the ones, being moved out from cache progressively, and the new ones are getting loaded as they are being used, right? The other kind of scenarios where you're seeing, for example, multi-armed bandits, right? So if you see, that's one of the mechanisms to deploy a large number of the models, where you don't want your one big monolith model to handle all kind of requests. For example, if you're doing speech-to-text translation, I mean, sometimes the speech files you get is like gigabytes in size, and sometimes you get KBs or MBs, right? And if you're loading up that huge monolith model for everything, even if you're getting kilobytes of speech or megabytes of speech, you're not doing justice to the underlying infrastructure. You probably want to, in case of multi-armed bandits, you have different models which are handling based on different sizes. For example, in that case, if this amount of speech is very less, the model which wants to handle is, has much lesser features and much lesser capability. Sometimes, you need to be able to translate to 20 languages. Sometimes the need is to translate to only one language. So again, even though the functionality is same, you don't want to be loading a model which translates to 20 languages for that simple request which just needs a translation in one language, right? So in a lot of these cases, because you are employing these multi-armed bandits kind of scenarios, you have that need where multiple variations of these models are running and ready and registered to handle depending on the kind of request which is coming in.
Got it. Sorry, just one more question. So in one of the diagram you were showing where you show the architecture, so in multi-model case, we are loading multiple model in a single pod, right? Multiple containers, single pod. So from Kubernetes aspect, is this fixed? What I mean to say, like you running 4 containers in one pod, and if you deploy, let's say, 100 more models, is it going to dynamically insert containers in the pod, or it will, how it get readjusted? Do you get my question?
No, if you can repeat this once more.
So when you're running multiple containers in a single pod, right? Let's say 10 containers per pod, and when I'm saying container, that's one model each, right? You have, let's say, 1,000 model already deployed. Now you're adding 100 more models. So how do you rebalance those 100 model to, let's say, 4 nodes, multiple pods, right? So do they get inserted to existing pod as a new container, or you will be deploying new pods for that and rebalance rest of the 1,000 containers?
So there are 2 modes. Like, so one is like the original KServe mode, which is essentially, models are mapped to pods, right? So if you're deploying new models, they are essentially new pods in that context. That answer your questions, right? So in context of the KServe, which is, single model per container paradigm, whenever you're deploying a new model, they are getting into new pods. In context of model mesh, you have multiple models per pod, right? So essentially in that case, the way it is actually, doing that calculation, it's using 2 metrics, right? Which is the number of requests which are coming for a particular kind of model, plus the cache age on a particular pod, right? So if a model is being used heavily, it will probably place it on a pod, which is not overloaded, right, in that context. But here, it's not provisioning a container per model, right, in context of model mesh, right? And that is how we are actually getting past the Kubernetes limitation, because the single model per container paradigm, if you have to scale, you are either using KPA from Knative, right, which is request-based scaling, or you're using horizontal pod scaling. But in both these cases, you essentially have to scale the number of containers as the number of requests increase, right? That's the original case of paradigm. In context of model mesh, you don't have to do that. The number of pods currently, when you just create that distributed LRU cache, the number of pods are static, right? That is your starting cluster capacity. And when the requests are coming, then it's using that capability, how much cache space I have, which are the pods where the models are loaded, which are not loaded, which are the ones which have been used in, which are the least recently used, which ones I can kick them out. Now, if that LRU cache gets filled up, it's total at a capacity, then you can, employ more advanced techniques like KPA and HPA-based auto-scaling, right, which is now provisioning new pods, right? But that's the secondary mechanism here, right? For the most part, as I mentioned in this case, like, on an 8-node cluster, we are able to run hundreds and thousands of these models, right? So majority of the use cases, you won't even need to hit KP or HPA if you have done the right sizing. Thank you. Go ahead.
For Model Mesh, are you changing any part of your architecture? Are you still using Knative?
Good question, right? So, okay, before I answer your question, right, so one of the things which we can see, like when we ran the last one, right, so this one showed now cache miss. Now, a cache miss happens because you see why it happened, like the cache, serving runtime cache usage, it actually hit its capacity at some point. A cache miss happens when a request comes in for a model and the model is not there loaded in the cache. So that's when it loads new model. Now, when it loads new model and there is not enough space in the cache because it actually hit the capacity, it unloads few. So as you can see now, the unloading rate is there. So it has been able to push out some of the models from the cache and load new models, right? And that happened because there was a cache miss. Okay, now to answer your question, are we changing the architecture from Knative? So I think in general with KServe, the vision of the project is to actually do more with less. And when we say do more with less, we essentially want to leverage Knative where it shines. Otherwise, if we can take the native Kubernetes capabilities and provide all these capabilities on top of it, we essentially want to do that, right? So now there is a raw mode available. Even if you don't use Model Mesh, let's say, you just go to KServe. There is a KServe raw mode which gives you the basic capabilities. Now you can deploy it on Kubernetes natively. You don't need Knative, right? But Knative is available, and all the full-blown capabilities of KServe are only available with the Knative version. Like when we are talking about transformers, when we are talking about explainers, all of those advanced capabilities, the canary rollouts, they are only available with the Knative version. But now we are moving forward and making sure more and more of these capabilities